But let me grab some water. But some others did not know how a chip is fabricated. So I thought I will do the most boring lecture in electrical engineering ever. So anyone who is doing masters in VLSI or chip design people? There is no chip designer here. So all chip designers hate this lecture. I did as well. Because this is purely materials. This is how chips are made. This is one process after another process after another process. And generally this lecture is the best lecture to go to sleep. Okay, so just before, this is why I'm doing it before lunch, not after lunch. But I'm doing this lecture not just to tell you how sensors are made, but also to introduce you two different aspects of it. One is, because we can make cheap sensors, and you have 3 or 4 mobile cameras on your phone, right? Your phones also have a gyro, it has maybe even a temperature sensor, an infrared sensor. This room might have carbon dioxide sensor. And that was a problem we did, and it's a problem of our own making. So we can make large number of sensors who then produce a huge amount of data. So good old way of directly measuring temperature from one sample and saying, yep, it's 30 degrees Celsius, it's hot, is no more true, because we have a large number of sensors in any system. So we will see what to do with data which is coming out of a large number of sensors in a production system, which is our system. Okay. So to do that, I will first introduce how chips are made, what sensors go into this, what data they are producing, how many of them are there, and then you will immediately see there is no way on earth we can process them by ourselves. We need some sort of machine learning there. So we'll do a very quick introduction to the kind of machine learning system we use. In the second half of the day, now remember, when I started talking about a robot, I said we have got sensors, but we also have this thing. So we need to make that thing as well, which is the head, not the skin. Right? And head will be some form of a learning system. So in the second half of the day, those who already have done a course in artificial intelligence or machine learning, it will be a very basic course. We'll just see what is a perceptron, how it behaves. But we'll immediately see how do we make a perceptron. So most computer science people generally assume that the hardware exists to run their deep learning algorithm. When the hardware doesn't exist, they just use a GPU cluster, a data center. There lies some problem. Do you know how much energy a data center consumes? So last Google's model, or so last natural language model paper which I read, the energy it consumed to train was more than the energy needed for a transatlantic flight. So you can fly 600 people from here to UK in less energy than it takes to train one neural network model. Now these days we are hearing a lot about artificial intelligence, deep learning and all that. If every problem is solved using deep learning, we do not have that much energy in the world in terms of power consumption. Right? And we will see why it is consuming that much power and what we can do to reduce it. Remember, our field, electronics engineering, we started as big computers. Remember in the good old days, history of computer you would have guys have learned, right? Computers used to be as big as the room or as big as an apartment. Actually, the first time one of the computers was powered on, it brought down the electricity of the whole city down. They were that big machines. So we went from that big machines and we kept on making them smaller and smaller to this. I mean, this has more computing power than early massive computing machines. Our computer science colleagues don't like this. So they are going backwards to big machines. Their machines are data centers, centralized machines somewhere else. And that for physical people like us is a problem. If we have a data center running for every institute, every city, it will require a huge amount of power. We can't provide that much energy. So we need to start thinking, if we go down the same route, we need to design our machine learning system in a slightly better fashion than ones we are designing right now. Because right now, the hardware which we are using, GPUs were not designed for running neural networks. They were designed for displaying high-speed graphics on computers. We are now stacking these GPUs to do these multiply and accumulate operations. So that will be our next border or next fence for electronics engineers to cross over, is to design new computing hardware, new chips which can do all of this neural network on a chip rather than a big cluster of systems. But before we do that, we need to see how we make our current chips and what the problems are there. Okay? Whenever you guys want to take a break, do let me know, because this is now my territory. I can keep on talking it for hours and hours. The paper to read is a paper by Rebecca Bush, one of my PhD students. What we're interested in is, I'll be telling the story from a slightly different angle. So we make chips. Not all the chips work. Right? Generally, we make chips in a wafer. So there will be a big round circular structure, and we'll be making square chips there. Some of these will not work. Now, the other day we looked at manufacturing of chips as a costly business. We're looking at billion-dollar investment. If some of our chips don't work, that's a wastage. So ideally, we would like as many of our chips to work as possible. That unit is called yield. What percentage of my chips are functional? Okay. To understand how a chip is being made and how we can predict what percentage of my chips are going to work, we will take the simplest circuit possible. All of you know what an inverter is, right? There is an NMOS below, a PMOS on top, and if you give 1, it becomes 0. If you give 0, it becomes 1. A low voltage becomes high voltage, a high voltage becomes low voltage. So a very simple circuit like that. Now the reason why we can use it is most of chip design, except for analog people, is a combination of transistors in one form or the other. We looked at image sensor design, there was 3 transistors. Here we have one of each, NMOS and PMOS. If we can understand one of each, we can make any circuit possible. Now the physical layout I explained to you kind of looks like this. If I do a vertical cross section of a chip, if I cut the chip one way, what we will see, there will be a P substrate and then either a P well or straightforward N-type diffusion. And there we are forming an NMOS type transistor. We will have a small oxide followed by polysilicon, followed by metal, and then on the N well we'll be making P-type structures. Remember that the other day somebody asked, why is the diffusion red? In this color, the diffusion has been selected as N, as green, and P-type diffusion as whatever color this is. I'm partly colorblind. I can only identify red and everything else is boring. Okay. Now, to the foundry people, and this is metal, the blue lines is the top, is a metal which is just connecting. So this metal is connecting from here to here. And we separate these with these dotted lines. These are just oxide. They are dielectrics which is separating this. Right? So this is what, when I ask my foundry to make an inverter, will make it. But we have done a very good thing in microelectronics world. We have separated manufacturing from design. So electronics engineers don't care about how it is made. Metallurgical engineers don't care about what they are making, as long as we give them a design. Okay? By now you would have learned that I abuse all of the departments of engineering except mine. This is the training of our Warangal to me. We are best and full stop. Okay. So let's see, in order to make this, what do we need? So generally we start from the bottom. We start from the bottom and then we deposit things on top. So we need that P-type thing between the P-type substrate. So we need a P-type substrate, and then from there we need to form these N-type diffusion or P plus type diffusion. Okay? So we need to do some form of diffusion or ion implantation. So we need to So if I start with a silicon, in order to form N-type, I'll be adding some sort of phosphorus, and to form P-type, I'll be adding boron gas. Okay. We also need a dielectric to form the gate. So this is dielectric is the gate, and also need dielectric to separate between different materials. Now to some extent we generally use a silicon dioxide as dielectric. Silicon is already available, just oxidize it, it becomes a good dielectric. Not for the gate. For gate we used to use silicon dioxide earlier, now we are using high K dielectric. Okay. Now we call this material MOSFET, metal oxide semiconductor field effect transistors. We don't use metal. In the transistor, metal has not been used for a long period of time. We use polysilicon. The theory of it is based on the work function. We are not going into this, so take my word for it. We use metal to connect between different structures. So we need metal and we need polysilicon to do that. In metal, historically we used to use aluminium. That was cheap, easy to make. Nowadays we use copper. Copper also has got good conductivity. Right? In past it was difficult to make, now we know how to do etching of copper. We could have used silver and gold as well, but gold diffuses in silicon. So CMOS foundries don't want gold to come anywhere near them. But once a chip has been made, then we use gold to connect to it, because gold is a very good conductor. Right? And this is why I could never understand why people waste gold in this, you know. They carry the whole bank on themselves. So my apologies to all of you girls, right? And people give gold gifts. I mean, if you go to a wedding, which I attended a few days ago, people are giving gold coins or gold bars. What's the use of that? That's just going to sit in a bank, right? I could make much better use of that gold bar. I can have so many good connectors made in my chip, but no. Now, this is the side view. That's not what we design. As designer, we design the top view. Okay, we give the top view to the foundry. So top view of this will look something like this, because we have no control on the side. Right? How much is going, that's defined by the foundry. How much dopants are going, how thick the layer is, that's not our control. We only determine how long and how wide our thing should be. So we basically tell to the foundry, okay, here in this region deposit diffusion, here this region deposit diffusion, this region deposit P-type diffusion, deposit this as my gate, no, okay. In this region deposit P-type structure, in this region deposit. So we basically tell to the foundry where to make what. Foundry doesn't care about whether it is connected properly or not. They will make it if you say make, I mean by mistake I could have just drawn a big metal wire here and shorted everything. Foundry will still make it. It happens to us quite frequently as soon. Now foundry, what the foundry does, there's a reason I have put them in different colors. Because remember, each one of them are being made in different height. So when I send them in different colors or in different layers, foundry divides these into individual mask. So they say, okay, that's where my N-well is going to be made. This is where my polysilicon is going to be made. This is where my diffusion is going to go. This is where my P diffusion is going to go. Finally, this is where my metal is going to go. And each one of these layers is made one at a time. Okay. Now, generally we use this term feature size to determine which technology we are using. So a 350 nanometer or 0.35 micron process is making the smallest structure of 350 nanometer. In past, it used to mean that's the smallest size of transistor, but you guys have seen it's no more the smallest size of the transistor. We also make these chips on a wafer, which is generally circular. For example, 300 millimeter wafer is now the standard, but if you take a 22 nanometer foundry in 300 millimeter, we are making 10 to the power 12 transistors. No chip needs that many transistors right now. So generally on one wafer we make many subchips and then we cut them. Okay. Wafer thickness is fixed, it's not in our hand. So a 300 millimeter wafer would be roughly 775 micrometer thick. For those of you who can't appreciate these numbers, your hair is 100 micrometer thick. So take 7 of your hairs and that's roughly the thickness of my wafer. Okay. Transistor size as well, take the hair thickness and cut it in 1,000 times or 100,000 times and you will get a transistor. Good. So let's make this thing. So if this was not boring, wait for the metallurgical part to come now. So start with an substrate. Generally the P-type substrate are already made for us. Should I take a break? Break lena hai? Or continue karna hai? Break? Okay. Even they realize that subject is becoming boring. Let's take a break and we'll come back and we'll see the fabrication, then we'll see where we need the sensors. Okay? So I will try to be a bit faster, but if you don't understand half of it, don't worry. It's more of an appreciation of what's happening. The next half will be more interesting. Okay. So we need to form a silicon dioxide first. First we cover the entire surface of the wafer with a dielectric material, because first it's an inverse process. Rather than making the thing first, we first protect the area where we don't want to make things. Right? So to oxidize this, we'll either use oxygen or water. And generally hydrogen, water is quicker, easier, but then you have to remove hydrogen out of it. So that causes more problem. So once we have done the oxidation, then we need to identify the area where we are going to put things. So we do it by some sort of a lithography process. So first we deposit photoresist, a material all across the chip, which is a UV sensitive material. So if you shine UV light on it, it will melt. Okay. And generally you spin coat the wafer. You put a drop and then spin coat it and it spreads out, and then you have got wafer all around it. And you have different type of photoresist. Some are positive, some are negative, of less interest to us. Then what you do, now you knew this was the area my designer gave me to make the N well, right? The mask, the first mask is there. We shine UV light through it. Okay. So all the photoresist below this, that softens up. Essentially we cut a structure like this. Okay. So once we have done this, now we need to remove the oxide below there, because we are going to form N well here. Right? We are going to diffuse some material and there. And this is done through a process called etching. Now etching is a harsh process. You pass hydrofluoric acid and then that starts eating away the material. And then you have to be very careful. If you allow it for too long, it will start removing the silicon there as well. Now this is a wet etching process. You also have a dry etching process. Okay. So once you have done that, you then use a piranha etch to remove the rest of photoresist which was left. Now this silicon dioxide is going to protect the rest of it from being formed. Okay. And then we pass some dopant gas, arsenic or phosphorus, at generally high temperature, 800 to 1200 degrees Celsius. So that dopant enter the silicon substrate and it go from P-type to an N-well formation here. Okay. Now this is the process which is a bit tricky, because based on the temperature, pressure of the gas, you could have lateral diffusion, things could go this way, and you can see there's already some, and even though I have drawn it as a rectangle, it never forms a rectangle. It's always a structure like this. Okay. Now controlling this is tricky, and this is where foundries have inherent recipe, what temperature, what pressure they are going to, and that control takes a long period of time. And once controlled, you don't change it, because you change, things could start behaving badly. Once you have done that, then you again apply hydrofluoric acid throughout the structure to remove the oxide. So remember it this way: oxide, oxidize your structure, put photoresist on it, Put the lithography mask, remove the photoresist from where you are going to form structure. Etch, remove the oxide where you are going to form the structure. Remove the photoresist, form the structure, and then remove the oxide. This sequence happens with every layer which we are going to form. Till now we have only formed N well. The same sequence repeats for every layer. Okay? Forming polysilicon, you form the gate first, and then you form the diffusion. I'm going a bit faster, so basically you're saying this is where you put diffusion, that's where N-type material will be formed, this is N-type, and then P-type material will be formed there. So it's pretty much similar process. Sorry, I should have told you what we are doing in N-type diffusion. So, you know what? So his diffusion, the structure is called diffusion. Remember in the layout also we called it diffusion. It's no more being used, diffusion, the process is no more being used to make these layers. We still call them diffusion for historic regions. The N plus is now being formed mostly by ion implantation in smaller geometry process. Okay? And the same process again. Repeat, repeat. Similar process, and now you dope with boron to make the P-type structure. We had made the N-type structure, now we make the P-type structure. And then you do deposit metal. Now in modern processes, you have roughly 5 to 10 layers of metal on top of that. Okay? Generally, modern processes also have dual well. We only formed an N well. We would also have a P well in modern process, and the transistors will be placed. The P N-type transistor will be placed in a P well, and P-type transistor will be placed in an N well. The other thing which I said we have changed, moved to copper. Now, I've gone a 5-minute quick summary of how to make a CMOS chip. There's a reason I went through this. Each wafer goes through several hundred different process steps before a chip is made. Think of it this way. We had 6 or 7 steps just to make N well. Right? If I have 12 metal layers, diffusion, oxide, I'm already in 12 plus 3, 15 into 6, 90 different steps. And I have taken a very simplistic approach of making this. Right? Each one of these steps can induce an error. What if my boron went too high? My doping concentration changed. My metal got deposited where it should not be, which has short-circuited the circuit. Okay? So all of this have errors induced on its error. Now each process also have several parameters to control. Temperature being a very good parameter. If I'm say sending a gas, it will be the gas flow. If I'm spinning it, it will be the actual speed of spinning. Now we generally monitor each one of these parameters. So we measure, so remember sometimes we are heating the wafer to 800 degrees Celsius. Sometimes we are sending hydrofluoric acid, and there the time becomes a factor. How long am I putting this thing in hydrofluoric acid? So all of these we monitor very closely, and we have sensors to measure each one of these parameters. Okay? And after each step, we also measure things like how much things have been deposited. So we do layer measurements there. As you can very quickly see, I have 100 process steps. In each step, I have got about 50 different sensors. I have 5,000 different data sources, not data points, data sources. Right? Temperature sensor, pressure sensor, timing monitors, and so on and so forth. So, and now we are collecting a time series data of this. Right? Over a period of time, look, if we started hydrofluoric acid formation there, the temperature was, and temperature doesn't remain constant. In any place, none of these remain, they are fluctuating. Okay? Taking this whole data as a whole is virtually impossible to do any processing. Foundries do collect this data, but And we have this thing called fault detection and classification. I mean, there are some things which we know will go bad. If the moment we see the whole chip has been covered with metal, that's it, forget it, throw the wafer. Okay? The problem happens is, what if we go through the entire process, make the chip? We can't test every chip. Testing every chip will take a long period of time. Testing one chip takes a long period of time. Think of it this way. I have, let's take a very simple chip, okay? 10 binary inputs and 1 output. That's a very simple thing. How many possible combinations of inputs are there? If I have just 10 lines, each with 1 or 0. 2 power 10 input possible combinations. Testing for all 2 power n is going to take a lot of time, even if I have an automated tester. Modern chips will have something like 144 or 244 pins. So applying different input condition and checking the output for each one of them will consume a lot of time. Modern chips also have inbuilt self-testing facility, particularly digital ones. Analog ones are tricky to have best. The process is costly, and we would like the yield to be as high as possible. More importantly, it would be good if we can tell how many of my chips are going to work from this data which we have collected. Now, one can imagine, if my production data changes, my output system will also change. Temperature change slightly, the dopant concentration would have been slightly different, the device performance will be slightly different. The other thing I keep on talking from last 2 days are no two transistors are exactly the same. So even transistor made on the same wafer, one side would have got more boron doping, the other side would have got slightly less boron doping. That will change the transistor. And then from one day I have made something, the second day I make something, there will be slightly more changes in the system. So we live within a certain tolerance of change. Right? If it changed by X%, I wanted to sell a chip at 2.2 gigahertz, rather than 2.2, it's 2.21, I will live with that. If the performance is 1.7, I can't sell it as 2.2. I might sell it as a 1.7 gigahertz chip. But if it's 0.5 gigahertz, forget it, I have to throw the chip away. Right? So it will be good if we can predict the yield. If we can tell without testing how many of my chips are going to work. Now it so happens, yield is a closely guarded secret. No foundry ever tells the number. Entire foundry business is a closely guarded secret. We know the steps. I told you the steps. We teach the steps. But what's the exact temperature? What's the exact pressure? How long it is done? It's a very closely guarded secret. Even the ones which I know of my fab, I will not tell anyone else. Because it has taken a long period. That is our intellectual property. Right? All chips are now being made by the same sequence. The devices are same. The material is the same. It's just the mix of process steps which is slightly different for each one of them. Okay, some of them have patents on high K dielectrics, only they can make few nanometer chips. The devices to make photolithography kit are export controlled, so only few countries can make them. So I can understand, but otherwise the sequence of steps are fairly well known. Okay, so which also means, so our task, we're working with a German foundry, was can we predict the yield based on the process parameters which we have collected. So we have a huge amount of data which we have collected. In past, we have also measured the yield, how many of the chips were within average performance parameter. So rather than this ability to measure, can I tell beforehand that if you go down this route, the chip will work or chip will not work? Can I predict the yield? The other issue is there are two things which are issue here. One is knowing exactly what percentage of my chips are working. 95% of the chips on this wafer will work. Or I put a threshold. If I'm making less than 90, that wafer is not worth selling in the market. Because even after the wafer has been cut, I need to dice, cut my chips, package my chips, and then test it. So it's going to cost me more. So if I can just say, you know what, this is below my threshold, don't test it, even that would be okay. So I have two problems now, and for computer science these two problems become the classification problem, good versus bad, or telling exactly what's the amount, how many of my chips are going to work. So the good versus bad problem is slightly easier. The regression problem, telling exact value, as you can see, would be slightly harder. It becomes even harder because no foundry makes their data public. It's not that you can, it's not like computer science image databases which you have, wherein most of you will, a number of you will do your project, run a new neural network algorithm and look, I can identify human beings in the picture. This data is not public. The only way you get is if you're working with a foundry, people like us who had access to some of this data. The classification problem has been studied by a lot of people in past. The regression problem has not been studied. So I'm going to give you an example of a problem set which we studied as to how it worked. Okay? So now I'm slowly moving you towards the brain part of the robot. Now before that we do just a quick summary of the kind of algorithms which are there. So have you guys done data structures in your bachelor's? Right? So you have learned about trees, decision trees. Smile on some of your faces says yes, we remember hearing that word. So we would be using a very simple structure called random forest, which is essentially a combination of very small classification trees. So you make large number of classification trees. Each tree tries to classify the data. And in the end, you do a polling. If majority of my tree says the data is good, you say the data is good. So rather than making one large structure, you make several small decision constructs. It's like asking all of you guys, is my lecture boring? If majority of you say it's boring, then it is boring, right? So that's what we are doing. We are not having one expert classifier, we are having multiple small expert classifiers. Okay. I will not delve you with how random forest is made. It is on the lecture slides online and you can have a look at this. There are other algorithms like k-nearest neighbors as well, which basically try to look at how many people are close to me. If I think this is good, how many of them are in this basket and how many of them are in the other basket. You just try to find in a space how many of them are nearer by. Anyway, I will jump into the data to show you how complex this can be. So we looked at 35,336 wafers which were made over a period of 6 months, okay, in a 350 nanometer auto foundry. So the chips were made for automotive production. Now automotive chips are always made 1 or 2 generations behind the commercial chips, or many generations behind the commercial chips. You know why? So all moving things like aeroplanes or cars, we don't use the most modern chips, generally speaking. The ones which are used in consumer electronics. Could you think of a reason why? There are few problems in modern chips. They have not been tested for long enough. You buy a mobile phone for 3 years. You don't buy a car for 3 years. Right? You don't buy an aeroplane for 3 years. If your mobile phone hangs, it hangs. You don't want your aeroplane to hang mid-air. Right? So you don't have the luxury of errors introducing the Simpson. The other thing is this, a number of our chips, an automotive and this face very high temperature. And think of the sensor which is sitting next to the engine looking at the oil level. Temperature could easily go 300 or 500 degrees Celsius. That's not the same temperature which your chips go. Okay? Unless by mistake you end up cooking your chips or putting your trousers, your mobile phone in trouser and putting in the washing machine. Okay. Good. Now, at this point you might say, okay, 35,000 wafer, each wafer having loads of data samples. Now this is where the real data becomes problem. Not all the time data is present. some of the sensors could have become switched off at that time, or they were giving erroneous data. When you have large number of sensors, you can't expect all of them to be giving true data at the same time. Okay? So there were data missing as well. And this happens because a number of other factors. Okay? And not every machine gives the same sensor data. So if I have, say, an etching machine, I thought it had 5 sensors. In one run, I got the data from all the 5 sensors. Another run, I only got 3 sensors which produced my output. Okay? So a vital step in almost all of these steps is to pre-clean the data. Now I have got a huge amount of data here. Let's have a look how much data I have. Oh, I haven't given the data number here. Okay, will come the data number anywhere soon. So we could not deal with these large number of sensors. We had roughly 650 different parametric steps, and we wanted to come up with one output here. 650 input measurements, one output, good or bad. That's it. That was too large a space to train a small neural network. If you're running a neural network on a GPU cluster, then that's perfectly fine. So we tried some data processing, and we looked at a wrapper feature selection method to extract what are the prominent parameters, which parameters cause the most change in the output. And we reduced it to about 323 parameters. Okay. Even that was heavy. We then started doing principal component analysis or Boruta analysis, which again we looked at which of these input. Now we are looking as parameters. We don't care whether they're temperature data or pressure data. They are numbers. So from one of these numbers, I'm trying to get an output. One output will be good or bad. Another is yield. Is it 90% correct, 80% correct, 70% correct? So I looked at this comparison matrix, and Rebecca found that a large number of these sensory data, or a good number, were actually not causing much change to the output. By their internal actions, yes, but individually they are not causing much change to the output. There were some which were doing big change, the green ones, and there were some which were in between. So we took this data and we iteratively kept on checking. So what if I remove this data point? Does it look still valid? If I remove the other one, does it look still valid? If it doesn't, then I put it back. So we ended up with about 190 odd data samples. Okay. Now each one of these, so remember a chip is going through multiple processes. In each process I have 320 data samples, which I have reduced to 190 data samples. Now the sooner I can tell that my wafer is going to go bad, the more money my foundry will save. It will stop the rest of the processes. Okay? So if I can just tell after the first process, hey, this sample is not good, and there's no direct relationship. It cannot say that one temperature caused the wafer to fail. It could have been a sequence of events which would have led the wafer to fail. Okay? So this is the kind of our result after training this neural network, training this random forest system. Now the dots are, so on y-axis I have the obtained yield which I have obtained. On the x-axis I have predicted yields. Ideally speaking, it should have been a straight line, because some of these chips were measured. Of course, we're not going to get straight lines. What you can see for things which are good, high yield, I've got a very good prediction. These are going to be high yield. For the ones which are bad, I cannot find. I mean, ideally this point should have been here. So the predicted yield was, say, 85%, and I was getting 81% kind of thing. But what I'm okay in predicting is this is going to be a bad wafer. I cannot tell that 60% of the chips will work, but if my cutoff threshold is 80%, anything below 80% is bad, I'm okay in telling good versus bad wafer. This is after one process step, right? We were looking at a system with 4 processes, one after. So even after one process step, I can say I can identify 99.37% of the good wafers and 97.98% of the bad wafers. These numbers look good, they are not good. So if my 2% of my bad wafers. Remember, I had 65,000 wafers, right? In 65, each wafer would have got roughly 1,000 chip. So 65,000 into 1,000 chips. Okay, I did wrong prediction on 2% of these. So 2% of 65,000 will be roughly 1,200 ish. 1,200 into 1,000. I'm sending 1.2 million bad chips in the market. Okay. So despite the fact from a computer science prediction point of view we are very good, you can pat on the tab. You look at the actual number, things are still problematic. When you look at all process steps, we of course significantly improve. Now we can predict 99.38% of good chips. So we only miss about 0.6% of the wafers. So few wafers we missed, and 98.78% of the bad ones. So we are doing much better approximation when it comes to that. Of course, one question which we were asked is, can you do the inverse? Can you now tell me which process step to improve to get a good yield? Or I'm going down the bad design, can I change something later on to improve the process to become good yield? We tried that and miserably failed. What we could say was that if something has gone down this route, whatever you do, it will not improve. But we cannot predict the exact amount of yield till now. There's a work in progress. This is not the final work, but the inverse solution we have not been able to answer till now. So given a set of sequences, I can tell whether it's going to be good or bad, but then to say which one or which few of the parameters to change to get a better yield is still a very difficult question. And you can imagine, I started with something like 600 different parameters. I've got one output. From one output going back to say one of these 650 or 5 of these 650 is challenging. Okay. Now, I went through a very quick summary of how to make chips and how we did one work on predicting the yield. That looks good, but it still required a good amount of computation power. It runs overnight. I cannot tell live as my data is coming that, hey guys, stop. And that's the problem. A large number of artificial intelligence algorithms cannot work live. So I went quickly here, and then I will also go, if I can. These are going to be high yield. For the ones which are bad, I cannot find. I mean, ideally this point should have been here. So the predicted yield was say 85%, and I was getting 81% kind of thing. But what I'm okay in predicting is this is going to be a bad wafer. I cannot tell that 60% of the chips will work, but if my cutoff threshold is 80%, anything below 80% is bad, I'm okay in telling good versus bad wafer. This is after one process step, right? We were looking at a system with 4 processes, one after. So even after one process step, I can say I can identify 99.37% of the good wafers and 97.98% of the bad wafers. These numbers look good, they're not good. So if my 2% of my bad wafers, remember I had 65,000 wafers, right? In 65, each wafer would have got roughly 1,000 chip. So 65,000 into 1,000 chips. Okay. I did wrong prediction on 2% of these. So 2% of 65,000 will be roughly 1,200 ish. 1,200 into 1,000. I'm sending 1.2 million bad chips in the market. Okay. So despite the fact from a computer science prediction point of view we are very good, you can pat on the tab. You look at the actual number, things are still problematic. When you look at all process steps, we of course significantly improved. Now we can predict 99.38% of good chips. So we only miss about 0.6% of the wafers. So few wafers we missed, and 98.78% of the bad ones. So we are doing much better approximation when it comes to that. Of course, one question which we were asked is, can you do the inverse? Can you now tell me which process step to improve to get a good yield? Or I'm going down the bad design, can I change something later on to improve the process to become good yield? We tried that and miserably failed. What we could say was that if something has gone down this route, whatever you do, it will not improve. But we cannot predict the exact amount of yield till now. There's a work in progress. This is not the final work, but the inverse solution we have not been able to answer till now. So given a set of sequences, I can tell whether it's going to be good or bad, but then to say which one or which few of the parameters to change to get a better yield is still a very difficult question. And you can imagine, I started with something like 600 different parameters. I've got one output. From one output going back to say one of these 650 or 5 of these 650 is challenging. Okay. Now, I went through a very quick summary of how to make chips and how we did one work on predicting the yield. That looks good, but it still required a good amount of computation power. It runs overnight. I cannot tell live as my data is coming that, hey guys, stop. And that's the problem. A large number of artificial intelligence algorithms cannot work live. So I went quickly here, and then I will also go, if I can